Welcome to Boson Buzz, where we dive into the coolest scientific ideas and breakthroughs shaping tomorrow's world. Robots are engineered for some of our world's most demanding and critical jobs. They venture into radioactive disaster zones like Fukushima, assemble complex machinery in automated factories, and even assist surgeons in performing delicate life-saving operations. But for all their incredible strength, precision, and computational power, they share a critical weakness with any other machine. They are inherently fragile. A sharp piece of rubble, a falling tool, or even just the prolonged wear and tear of constant operation can cause a cut, a puncture, or a crack in their structure. For a traditional robot built from hard metal and rigid plastic, this damage often means an immediate mission failure. The robot must be retrieved, if possible, and then undergo costly, time-consuming, and highly specialized human repair. This inherent vulnerability, this inability to recover from even minor damage, severely limits their true autonomy and long-term reliability in unpredictable environments. But what if a robot could respond to injury not by breaking down, but by healing itself, much like a living organism repairs a cut on its skin? This is the ambitious goal of a revolutionary new field, one that aims to create robots that are not just strong and smart, but fundamentally resilient and self-sufficient. The key to creating a self-healing robot lies not in its software or its processors, but in its very substance, in the materials from which it is physically constructed. Instead of being built from traditional hard metals and rigid plastics, these next-generation machines are primarily built from soft, flexible, and compliant materials, a field known as soft robotics that takes direct inspiration from the biological world. These robots often resemble natural forms like octopus tentacles, caterpillars, or human muscles, moving away from the rigid, jerky motions of industrial arms towards a more organic and adaptable form of locomotion. Their soft, compliant bodies allow them to perform extraordinary feats that are impossible for rigid machines. They can squeeze through incredibly tight, confined spaces, handle delicate and fragile objects like a ripe fruit or a human organ without causing any damage, and move with a fluid, natural grace that makes them far safer to work alongside humans. However, this very flexibility and softness that grants them such unique abilities also makes them more vulnerable to punctures, tears, and cuts from sharp objects they might encounter in their environment. To solve this fundamental paradox, scientists looked to the ultimate model of resilience and repair, biology itself. They asked a profound question: what if we could give these soft machines a version of a circulatory system or regenerative skin, effectively endowing them with one of life's most fundamental and powerful gifts? This line of inquiry moved the field from simply mimicking the form of nature to emulating its most robust functional principles. The answer lies in a class of specially engineered smart materials known as self-healing polymers. These are not simple, passive rubbers or silicones. They are dynamic materials with a built-in, active repair mechanism designed into their chemical structure. The most common and visually dramatic method involves embedding the robot's soft body with a network of tiny, liquid-filled capillaries, much like a synthetic, microscopic circulatory system. These tiny vessels are filled with a special chemical agent, a liquid monomer. When the robot's skin is punctured or sliced, these microvessels rupture at the site of the injury and release their liquid payload directly into the wound. Upon contact with the air or with a catalyst chemical that is embedded in another part of the material, this liquid undergoes a rapid chemical reaction. It polymerizes, solidifying almost on contact to form a new, strong, and seamless seal that chemically binds the damaged edges together. It is a synthetic scab, a biological-inspired repair that heals the wound from the inside out, restoring structural integrity without any external intervention. The practical implications of this self-healing capability are profound and far-reaching, opening up dramatic new frontiers for robotics across numerous fields. A search and rescue robot, for example, could navigate the treacherous, unstable, and debris-filled landscape of a collapsed building in the aftermath of an earthquake. It could sustain a cut from a piece of sharp rebar or a deep abrasion from shattered glass, and yet continue its critical mission to locate survivors without interruption, healing its wounds as it goes and maintaining its operational integrity when it is needed most. an exploratory robot on a distant, uncharted planet like Mars could survive the harsh, abrasive environment far longer, healing minor scratches and punctures from sharp rocks and fine, sandblasting dust entirely on its own, greatly extending its scientific operational life and maximizing the return on a multi-billion-dollar mission. In our own homes and workplaces, a soft robotic assistant would be far more durable and inherently safe to interact with, capable of recovering from accidental bumps, scrapes, or even more significant damage that would permanently disable a conventional robot. This self-healing capability represents a giant leap towards true long-term robot autonomy and reliable deployment in the real world. It dramatically reduces the need for constant human maintenance, retrieval, and repair, and it allows machines to operate reliably for extended periods in complex, unpredictable, and remote environments where damage is not a rare possibility, but a near certainty and an expected part of the mission profile. The magic of self-healing polymers is rooted in sophisticated chemistry and material science. Researchers have developed several powerful approaches to achieve this capability. One method, as described, is the capsule-based approach, which is excellent for repairing specific, localized damage. Another, even more advanced method involves intrinsic self-healing polymers. These materials are not filled with capsules, but are designed with dynamic chemical bonds throughout their entire structure. When a cut occurs, these special bonds are broken. But if the two damaged surfaces are gently pressed back together, often with a slight amount of heat, these bonds can spontaneously reform, essentially zipping the material back together at a molecular level and leaving little to no trace of the original injury. This process can sometimes be repeated multiple times in the same spot. Scientists are continuously working on improving the speed of this healing, the strength of the healed bond compared to the original material, and creating systems that can function in a wide variety of environmental conditions, from the freezing cold of the Arctic to the dry heat of a desert. The future of self-healing robotics extends far beyond the incredible feat of simply sealing cuts in a piece of silicone. Researchers are already working ambitiously to create integrated, multifunctional, and comprehensive self-healing systems. Imagine a soft robotic gripper that not only heals a tear in its structure, but can also automatically restore electrical conductivity across the newly healed wound, allowing power and vital data signals from embedded sensors to flow uninterrupted once more. This is absolutely crucial for the next generation of robots that will have sensors, processors, and actuators distributed throughout their soft bodies, creating a nervous system that must also be resilient. Another exciting frontier is developing materials and architectures that can heal from larger, more catastrophic damage, or even slowly regrow entire missing sections, much like a starfish or a salamander can regenerate a lost limb over time. Furthermore, scientists are exploring how to integrate these self-healing properties directly into the artificial muscles and actuators, the very components that make the robot move and exert force. This would create a machine that could recover its core functionality and mobility even after the mechanical parts that drive it have been compromised, leading to truly fault-tolerant systems. We are rapidly moving towards a future where a robot's durability and operational lifespan are not fixed properties determined at the factory, but a dynamic, ongoing, and self-managed process of maintenance and recovery, blurring the line between machine and living organism. While the technology is still primarily in research and development laboratories, working prototypes have already convincingly demonstrated the ability to fully recover from significant damage, returning to nearly 100% of their original strength and functionality within minutes or hours. The current challenges for engineers involve speeding up the healing process to near instantaneous rates, increasing the strength of the healed bond to match the pristine material perfectly, and scaling up the manufacturing of these sophisticated polymers to create larger, more complex robots. But the path forward is undeniably clear. We are moving from an era of brittle, high-maintenance machines that fail with a single point of damage to an age of robust, resilient, and enduring robotic partners. By blending the timeless principles of engineering with the powerful strategies of biology, we are creating a new generation of machines that can endure, adapt, and recover from the challenges of the real world. We are not just building robots, we are endowing them with one of life's most fundamental and powerful characteristics, the incredible, persistent will to heal. If you found this as fascinating as I did, do me a huge favor and hit that like button. Share this video with anyone who loves science or just cool, futuristic tech. And of course, if you want to stay updated on this and other amazing breakthroughs, make sure you subscribe to the channel. Thanks for watching, and I'll see you in the next one.